everyone, and welcome to the 2024 Gardner Lecture. I'm Julie Shah. I'm the department head here at AeroAstro. This Gardner Lecture is made possible by the bequest of the late Major Lester D. Gardner, a member of the MIT class of 1898, to sponsor annual presentations on aeronautical history. An officer in World War I, Major Gardner was the recipient of numerous aeronautical awards, including the Daniel Guggenheim Medal in 1947, given for outstanding achievement in advancing aeronautics. He had a long and storied career, establishing a publishing group responsible for 4 aeronautical trade publications, including the predecessor of Aviation Week. He was also a founder of the Institute of Aeronautical Sciences, which would eventually evolve into today's AIAA. Major Gardner's interest in MIT and our department continued throughout his life and lives on not only in the memory of the Gardner Lectureship, but also the Hunsaker Professorship, which he helped to establish. Over the years, our Gardner lectures have included Grover Loening, Igor Sikorsky, Yvonne Brill, Neil Armstrong, Robert Siemens Jr., Gwen Shotwell, John Langford, and Pam Melroy, to name a few. This year, we are honored and excited to welcome 4 speakers to deliver the Gardner Lecture. These are 4 Course 16 alumni who have gone on to become leaders and innovators in their field. Together, they decided to give a joint lecture on a very specific topic, which they are calling Aviation in the Age of John Hansman. R. John Hansman Jr. is the T. Wilson Professor of Aeronautics and Astronautics. He directs the International Center for Air Transportation, as well as the Laboratory for Aviation and the Environment. Over the course of his 40-plus year career, John has contributed to the field of aviation in a myriad of ways through research and technical papers, new patents, and novel approaches. But perhaps his greatest contribution to the field has been through his mentorship of entire generations of academic and industry leaders. Our Gardner lectures wanted to give us a sense of John's tremendous sphere of influence, his impact on modern aeronautical history through their own expertise. So a few words about our speakers before I turn it over to them. Amy Pritchett is the department head of aerospace engineering at Penn State University. Her research focuses on the interaction of technology, humans, and safety in dynamic, time-critical, and safety-critical environments, including human-robot interaction in space exploration, human autonomy teaming in aviation, novel flight deck designs, and manual control. Craig Wanke is chief engineer for the MITRE Corporation's Center for Advanced Aviation Systems Development and editor-in-chief of the Journal of Air Transportation. Among his accomplishments include leading the development, field testing, and technology transfer of several capabilities now deployed as a part of the FAA's operational traffic flow management system. He is an AIAA fellow. John Paul Clarke is a professor of aerospace engineering and engineering mechanics at the University of Texas at Austin, where he holds the Ernest Cockrell Jr. Memorial Chair in Engineering. He's an expert in the development of the use of stochastic models and optimization algorithms to improve the efficiency and robustness of complex systems with a particular focus on aviation. And Brian Yutko is the Chief Executive Officer of Wisk Aero, a leader in the advanced air mobility market. His focus is on electric and autonomous aviation. Prior to joining Wisk, Brian served in numerous leadership roles at Boeing and Aurora Flight Sciences, managing various rapid prototyping and autonomous technology development programs. Thank you very much, and with that, I'll turn it over to Amy.
Thank you, Julie, and thank you to the Department of AeroAstro. It's a pleasure to be back and have a chance to give this storied lecture. Indeed, I have to multitask, and I have like 15 minutes to do it. In that, I want to reflect the spirit of the Gardner Lecture with a historical perspective. I would like to stay technical, as my former advisor taught me to do, and focus on the important technical aspects in aviation safety. And in doing so, I think we'll see that there is a common theme to the presentation, a name that keeps recurring in what I will reflect on as major achievements in aviation safety. So with this quick historical perspective, looking back to 1959, looking at the accident record of jet air transport aircraft, the numbers have now, safety's hard to define. We don't measure safety, we measure the opposite, accidents. And the accident rate has gone down to the point that I think we can argue the civil air transportation in the Western world is the safest system ever. Definitely the safest transportation system, but right now I'm ready to take on nuclear power as well. So, but to achieve this, to achieve the level of safety that is reflected with such a profound reduction in accident rates requires several different approaches. And the historic approach was to focus on single point failures. Make certain that you didn't have some unwitting accident. And looking back through aviation safety, we have those flashbulb moments, those accidents that we in the discipline remember profoundly and that the entire industry used to drive our new insights as they reflected what was going wrong. For me, perhaps the first snap bulb industry, and one that's really important to this more modern age, was United Flight 232 in July of 1989, where the fan disc in engine number 2, which was mounted in the tail, right above where the 3 hydraulic lines all joined together, needed to power the control surfaces, well, the fan disc blew. And while there were many things leading up to the fan disc blowing apart and blowing through the hydraulic lines, it, in the end, highlighted that at that instant in flight, given you had a fan disc that had design and maintenance issues, that in flight we had a single point failure. Now, I particularly recall this because I was a freshman in what was then called the MIT Aeronautical Systems Lab. We gathered around this thing called the TV and watched live news to watch it. And the McDonnell Douglas engineer who was briefing CNN was holding a schematic and pointing everything out, and his brass rat was going up and down in front of the national news as he described just how we had gotten to the point that one single failure could make an airplane, well, at the time they said it should have been considered unflyable. The second lesson that we learned that day is that in many cases, safety ends up being a factor also of people being able to come together and work together in new ways. For Denny Fitch to run back from his passenger seat and be able to work the throttles while the crew already in the flight deck flew around a while, learning to fly the airplane only with differential thrust and elevator trim, to the point that they had something roughly approximating a landing, and something where we would have expected everyone to not survive, to instead have 2/3 of the people survive. And this accident, we look back then on both lessons, the single point failure, but also the role in the crew on figuring things out. Now we'll go forward a little bit more. 1995, the Cali accident. An American Airlines 757 was en route from Miami, descending down to land into Cali. It's a tricky approach. You can see on the left the terrain where you would have to descend down into the valley to line up on the final approach to the land roughly to the south here. And unfortunately, the auto-flight system tried to, apparently thought it could fly through granite. There was no terrain information available to the pilots. And as I will talk about a bit more later, there's also a question of just what was available to the pilot for interpreting where their auto-flight system was going to take them. Now, this accident was in 1995, and one of the principal things that was called out was the lack of terrain situation awareness for the pilots. 1995 accident, 1993 study by Kuchar and Hansman looking at terrain situation awareness, developing those fundamental insights needed for Don Batewell at Honeywell and others to really develop the enhanced ground proximity warning system so that as the industry recovered from this accident, they were able to say, but there is a technical solution that we can implement. So it was this study in Building 37 in a part task simulator cobbled together with IRIX machines that I view as one of those key moments around the industry looking at what is possible in 1993 and being positioned when we actually had the accident in 95 to step in and to say, we have solutions. And with this, here's the data on jet aircraft accidents for the period 1991 through 2000. It's divided, each bar representing a different category of the major descriptor of the type of accident. In this case, look at the two big bars that we had in the 1990s, the leading types of accidents, loss of control, and next to it, CFIT, controlled flight in terrain. And the Cali accident is a major part of that big bar of the fatalities that we were seeing because pilots couldn't tell where the airplane was going relative to terrain. Let's skim forward to the most recent set of data that I have, 2013 to 2022. Can you find CFIT on there? It's down there. It's down in the noise. It's one of those small bars. And so we can see cases where some of these advances we can point to as having such profound impact, like the enhanced ground proximity warning system. That's the good news. The bad news is that how do you make a system safer than this? How do you address the more complex and interrelated accidents? For this, I would put out that you have to do many things all at the same time. As engineers, we normally start by looking at the single point failures, the reliability and redundancy, the fault tree. And this is necessary, but is not sufficient. Then we look at creating multiple layers of defense, robustness. And these layers of defense can include pilot training, procedures, and maintenance, and making certain that the pilot doesn't have the fan disc blow apart in the first place. Necessary, but again, not sufficient. And finally, we find that we have to also look at how we control the situation. And the levels of control, again, are operational control, traffic flow management, so you don't have a pileup of airplanes in the same sector. But specifically important is how do we control the situation right at the point of the incident, of the problem, the pointy end of the stick. Now, there's multiple layers of control, but hey, it's always fun to talk about autonomy and autoflight and to talk about how control automation has shaped the flight deck. So here's a picture of an aircraft designed and first flown in 1969. You can see that there's 4 throttles, 4 stacks of engine instruments, and there's even a flight engineer over here, a third pilot in the cockpit. So I hope you can guess, if you're in this auditorium, what airplane this was. And here was the redo, the Model 400 from the 1990s. It still has the same flight instruments, but now they're shown on a glass cockpit. It still has the 4 engines, but all the engine instruments are shown, again, on the glass screen. And instead of having a flight engineer, a third pilot, we have reduced the pilots from 3 being standard to 2. What the flight engineer used to do is now start and stop. The full authority digital engine controller is a full authority controller. There are things that we have successfully automated. But there are other things, like where do we want the airplane to go, that are very hard. And for this, I will return back to the Cali accident. And with the Cali accident, this picture on the lower right here is from the control display unit, recreated by the NTSB from the NTSB report. And why did the airplane try to fly through a mountain? Well, the airplane logic was suggesting go to waypoint R and then join the route into land at Cali. And the pilots had very poor understanding. What does this mean? Should I have even gone to point R in the first place? And the answer is no. And so here now, we're also starting to think not just about the single technology, but how do we get the parts to work together? How do we get the, particularly close to my own heart, how do we get the pilot and the technology actually working together better? And again, we can point to some things in this time in the 1990s where Eric Johnson and I met each other by doing a class project for Tom Sheridan and John Hansman, where we proved that in the Building 37 simulator, it was pretty easy for me to put the captains in what would be an innocent mistake into a steep descent into terrain, and most of them to not detect it until it was too late to pull up. And on the right, I'll show the vertical profile display, recognizing Sanjay Vakil, Alan Midkiff, and John Hansman here, that emphasizes not just where are you in space and time in a vertical profile, but where is the autoflight system going to take you with the way it's programmed right now. A display that I think we can now pretty much point to in the A380, 787, and other subsequent aircraft. So with this, we're working on many new questions about how human-machine interact. We haven't answered them yet. Aviation, I think of as the leader in aviation, in human factors. And for this, I point out that in 1951, it was in a National Academy study chaired by Paul Fitz looking at effective air navigation that posted this model, a model I wish that could be burned at the stake and tortured for its value that it doesn't have, called "The Men Are Better At, Machines Are Better At." And I mind not just the genderized language, but the fact that it doesn't understand that the two of them need to interact, and it doesn't understand something fundamental about who ultimately controls the situation. For that, I think we should go back to the federal aviation regulations. Who controls the situation? The pilot in command of an aircraft is directly responsible for and is the final the authority as to the operation of that aircraft. And what does that mean? It means that as the captain, you engage the autoflight system. What do? There's a 1996 Simpsons episode. It says, once you engage this Navitron system, all you have to do is sit back and feel your ass grow. We're not recording this, right? I'm just quoting The Simpsons. Okay. But no, as the pilot in command, you now have to sit there and monitor it. How often do you need to monitor it? As fast as it can screw up. For an autopilot, that's pretty fast. And then you need to figure out when to intervene, and to intervene before it is critical. And this is not easy. Now that I'm a department head, I can assure you, monitoring and supervising and intervening is harder than just doing the task yourself. And yet this is the task that we are putting pilots into. To put them into a tough spot, we say that their role is shifted to monitoring. And yet, there were brilliant things said before in that 1951 report. The Mamba list was embraced by the controls and autonomy engineers as, yeah, I can get my machines to do these new things. And it's commonly cited. Rarely cited is what's on the next page. In 1951, they took the position that human operators are poor monitors, when all they have to do is watch the performance of automatic equipment. And so with this, we are at a very interesting time where we are seeing public-private partnerships in aviation safety, broad discussions throughout the industry talking about, wow, what do we need to do differently? Not just focusing on one system or one technology, but looking at broad operational principles. And so now moving forward to 2013, the safety alert for operators was actually recommending that we have pilots fly more often. Maintain not just the manual control skills, but we're now finding that you need those same manual control skills also to have the mental skills, the knowledge, the task ability to monitor in the first place and detect when something is not going right. Finally, bringing us up to the very latest stage, pointing out some things again from the national academies that we're working on, we find that the same names keep popping up in these national level committees that are coming together to look at the current state of aviation safety. In our overall review of the aviation industry's ability to identify safety issues, our summary is that there are many ways that we are monitoring air transport safety right now, as based on the tube and wing aircraft that are flying, the operational models that we have at this point. They span from single organizations to industry-wide teams like the Commercial Aviation Safety Team. They span deep dives on particular hazards to things that are monitoring system-wide. And in this, we now have the mechanisms in place to be jumping on any immediate issue and extrapolating forward. What do we think are the intermediate, potential near-term evolution issues? But the predictive is kind of hidden a little on the Rubik's Cube, is a little hidden off on the right. Predictive, how do we predict the safety of something that's never flown? Some new AAM vehicle that's brought in, or VSTOL aircraft flying with a very different business model, very different traffic density and traffic operations. For this, we need new methods and new timeframes. And this is in the face of all the amazing things that are happening in aviation right now. Each of these things we can look at going, wow, we can do new business models. We can have transportation that gets above the gridlock of Mass Ave. We can have new technologies that are so much more efficient. We can help with sustainability and climate. But at the same point, we also then say, and how do we predict the safety impact to maintain the safety level for things that we don't have that same weight of knowledge for? An interesting time, if I had an answer, this would have been a different talk. But as it is, I'm just saying this is where we are now with big questions left to be answered. And so I thank you, and I offer apologies to similar important technical advances in addressing aviation safety, including icing, wind shear, collision avoidance and detection, and so forth. Thank you.
I'm just going to switch this over. All right, hello. That was a great setup. Thank you. Okay, I'm Craig Wanke, and I'm going to talk about air traffic systems. There's a little bit of, well, obviously the relationship to safety is there. I'm going to say a little bit about myself in that it's relevant to this, which is I was here at MIT for 10 years, roughly, mostly working with John during that time. I took that experience to my work at MITRE, where we operate what's called the Federally Funded Research and Development Center for the FAA, which is where I've spent all of the last 31 years. And along that time, I spent a lot of time working with AIAA as well, as I'm sure you do, and I'll get to why that's important later on. I wanted to go back to, when I was preparing this talk, I wanted to go back to see some of the things that we did in graduate school, and I had to go find a paper that had a figure that would reflect what we worked on. That figure was glued together with glue sticks and pasted up to be photographed for a paper. But one of the accidents that Amy didn't talk about that were kind of in the news when we were in grad school were wind shear related accidents. And there had been a couple of them, a notable one, the Eastern accident, where the airplane was lost because it flew through a downburst from a thunderstorm. And so systems were being developed to alleviate this. And you see the terminal Doppler weather radar on the lower left, and other systems like the low-level wind shear avoidance system on the right. And the question was, how would we use these systems to stop these accidents? You'll notice no accidents have happened since then. I can't tie it directly to this work, although the TDWR has something to do with it. But in the process but my work was around how would you design a system to detect, synthesize data, and alert the pilot of these things. And in so doing, it formed everything I needed to go forth in a career and looking at human decision support in the context of aviation. And that's going to be sort of the theme of this talk. So human-centered design is one of those things. Something else I wanted to mention for those of you who are kind of in this stage of your career, the other thing that John taught me that was super important was that publishing is a way to actually execute on your entire plan, because you submit abstracts for things you haven't done yet, right? And then you have a deadline. And you're not being fearless enough if you never withdraw a paper. So it's okay to occasionally withdraw a paper. And finally, aviation is all about weather, also terrain, but also all about weather. And as I went on to my career working on the National Airspace System, I really began to appreciate all the ways in which that is true. Now, one of the things that I found as soon as I left MIT was that I was now at a company that was supporting the entire development of the National Airspace System, and I lamented the fact that the one course I never took in aviation at MIT was air traffic control. So I had to learn all of that. This is a diagram of all the systems that make up the U.S. air traffic control system. And it's an imposing system. So you can see the numbers there. I'm not going to go through them. And it's run by a team of 14,000 air traffic controllers and a number of other folks that handle the other functions, the air traffic management functions, and so on and so forth. And so anything that is introduced to this really needs to be carefully considered. Safety is the #1 priority, and as Amy noted, the current safety record is excellent. And so everything that needs to be introduced has to be compared to that record, which I'm sure Brian will probably get into this later. So over the 31 years since I graduated, a lot of things have happened in this system. There's something called the Next Generation Air Transportation System was deployed, and this revamped all of the primary automation systems. There's a lot of jokes back in the day about how the FAA ran systems on vacuum tubes. To my knowledge, there are no more of those. I'm not entirely sure. There may be in Alaska some weather systems that have vacuum tubes in them, but for the most part, the system has been deployed, and we move a lot more people and freight today than we did back when I graduated, and the delays are generally not worse, which tells you it's working. So that's kind of the state of the art. Over the course of that time, and where much of my work was, is in that the science of air traffic flow management has changed radically. Back in the day, 31 years ago, the FAA controlled everything. Now there's a collaborative decision-making process where the airlines and the DoD and other operators take part in the management of the system, and that's been a major advance. Weather forecasts have improved, traffic management tools have improved, and so our ability to do more than just keep aircraft from hitting each other, but rather to make the whole system more efficient has improved. And we've gone to something called trajectory-based operations, and what this means in practicality is that when things get incredibly dense at an airport, we can manage the flow by time of arrival. And because of the deployment of GPS and other precision navigation systems, aircraft are much better at following those things, provided that the pilots are interacting with the system and not just watching it happen, right, as Amy was just talking about. So just briefly, you guys probably already know this, but I didn't know it when I left MIT, so I figured I would put it in here. Air traffic control is what people know, is controllers separating airplanes. It's a fairly exact science. It's well-defined. There are tools that have been deployed over the past 31 years, but fundamentally it's not that different than it was back then. But traffic management, where you're looking out, say, 30 minutes to 24 hours to plan against things that are probably going to happen, is something that has been evolving quite radically over that time. And it involves, many, many stakeholders. It's a bit of an art. And honestly, there are a lot of still unsolved problems in this. And so that's where I'm going to spend a good bit of the time in this lecture. So to get back to weather, aviation weather forecasting is challenging. It's one thing to know if you're going to hold a picnic that it's the 30% chance of rain this afternoon. You need much, much more precise weather to do anything with aviation. You need to know whether particular routes will be closed, whether airports will be closed, or will be impacted by low visibility. This is an example of the absolute state of the art in long-range thunderstorm forecasting. Each of those areas, which are hundreds of miles long, tell you that there's maybe a certain likelihood of thunderstorms happening and what the likely tops of those would be. Planning to this is not trivial, nor is it precise. And so the essence of the modern system is flexibility. You have a lot of tools to manage flows, and so the challenge is how do you react to something like this? Under 90 minutes, we know we can watch thunderstorms move, and we have a pretty good chance. So what I'm going to talk about are some of the tools that I've been involved with developing and applied my lessons that I learned here at MIT to help develop and deploy, and some things that we haven't solved yet. So one of the first things I got involved with when I left here was in trying to support this collaborative decision-making process by giving traffic managers what you would think would be a very simple thing. There's weather. We have a pretty good idea of where it's going to be. How do we know which airplanes are going to encounter it? And what do we do about it? So again, simple problem. They had no way to do this, right? You were doing this incredibly manually. And so all of this did, and we did this with, we actually put a trailer out at one of the centers and put a bunch of computers in it, and we let traffic managers come out and play with it, looking at the real data and do some tests, to get back to human-centered design. And come up with a system where you could draw a polygon or a line, and you could add a bunch of filters to it, and it could move. And what it would fundamentally give you in the middle of the screen there is a list of which flights were involved and how many were encountering it as a function of time. And what we found was if you give them something like this, and it was deployed in what was then called the Enhanced Traffic Management System, they would find a million ways to use it. And so this tool actually is the basis of a lot of the things that cause your pilot to say, while you're sitting on the runway in perfectly clear weather, we can't leave because of air traffic control hold. That's actually a good thing, believe it or not. But there are things called airspace flow programs that keep us from overloading sector controllers near these weather areas. And a whole host of other what we call traffic management initiatives that are planned by the use of these things. And one of the things I learned from this was that if you give people a flexible tool, they will find all kinds of innovative ways to use it that you probably didn't even predict. But the most important thing about giving any kind of tool to people who have essentially a full slate of work on their plate is that the first thing it has to do is save time. And that's what computers are good at. Like, have the computer do the things that are drudgery, the things that are difficult, right? But have it be an interactive part of the process. And this was a great example of that. The next thing we tried to do was say, okay, let's say you take some action, to move aircraft around that weather. What's the impact of that going to be? This proved to be a much harder thing to get designed appropriately and for them to do. So on the left there, you see a case where something called a national playbook play is being evaluated. That's a predefined set of routes that get around weather in certain places. And there is a whole virtual online book of those. You can actually look it up yourself if you go to the NAS status page on the web. But in this case, it's going to move, possibly hundreds of airplanes, and the question is, what will that do to the system? And so on the right is a system that was deployed that allows you to test that, and it tells you how many airplanes you're moving from one place to another. Without getting into detail, this is a tool for determining whether you have the right staffing in place, to handle this situation. From the time that this was developed to the time that it was deployed was 17 years. Which is on the long side. Typical, I think the average time to deploy a new feature to the NAS is about 10. But this is what happens when you're working with a system that has to work all the time. And it's an argument I get into with my military colleagues all the time on the other side of MITRE, where they can deploy something in 2 or 3 years, and the difference is ours have to work all the time. A military system can work 95% of the time and still be acceptable and still give you an advantage. And that's a huge difference for when you're working in an air traffic control system. The next step beyond this was to start thinking about systems that suggest solutions. And this is an example of one that we worked on, and it employed some NASA ideas as well. But basically, the idea would be, instead of having to develop those routes and do what-if examples to test them and so forth, you could actually identify, for each aircraft involved, what would be a reasonably optimal route to get around a weather situation, coordinate it. And then one of the big problems with rerouting is you have to collaborate amongst facilities. And so this would automate that coordination. Again, we did a bunch of human-in-the-loop testing and worked through it until they were satisfied with it and thought it would work. It was put into the deployment pipeline, and then the funding dried up. But it is a possible thing to do. It's still potentially on the list, so maybe someday we'll see something like this. But to date, we don't move aircraft one at a time. We move them in giant groups. So that's still the state of the art. And the last system I wanted to talk about was the problem of strategic TFM. The stuff that I was talking about before, you saw pictures of weather. That means we had either weather radar returns on there, or we had short-term predictions where you could actually draw, essentially where you thought the weather was going to move. But strategic TFM uses that initial weather picture that I saw, which is that I have a vague idea of where the problem's going to be 12 hours from now, 6 hours from now, whatever it is. And I have a bunch of aircraft that are going to take off and maybe spend 5 hours in the air. What do I want to do? There's a couple of problems with this situation. Number one, typically when humans are solving a problem, they rely on past experience. You never get the same weather day twice in the nest, really, right? And so it's very hard to learn from experience. The other is you have a bunch of stakeholders involved that have different objectives. The FAA folks want to protect their controllers so that they continue to safely handle the aircraft. Airlines obviously want to meet their schedule. DoD wants to execute their mission, so on and so forth. And so it's not clear what winning looks like either. So it makes it a hard problem to solve. So the way we do this today is that every 2 hours there's a teleconference where we argue about what the right solution ought to be and pick some set of solutions out of an infinite design space and then see how they work. And then 2 hours later, you go back and have another argument and work on the next thing. And so for years and years, we've been trying to design systems that would solve this problem. And the fundamental, you're looking at a picture here of the Air Traffic Control Command Center in Northern Virginia, where they coordinate this argument. And the data that they have is the weather forecast that you saw and some other weather forecasts. They have counts of traffic around the area. And of course, they still use those flow evaluation areas that I showed back when to kind of look at what traffic is where. But there aren't really any diagnostic systems to do that. So you can't have a talk today about aviation without AI coming into it someplace. And so this is where we're trying to apply modern artificial intelligence to solve that specific problem. And past attempts to solve this problem using previous kinds of technologies have generally failed due to the same reason that it's hard for humans to solve this problem, which is that it's very hard to draw conclusions about what worked in the past because you don't really have great data to work from. Modern machine learning systems, turns out, can piece things together pretty well from a whole variety of vaguely similar situations and draw better conclusions. And so for the first time, we think we've found something that can help people navigate this enormous design space. And if you just look at to give an example of what these kinds of problems are, I don't know, what's the time situation? I haven't lost track. We're good? Okay. So I'm just going to go to this, actually. To look at a real example, here's a very simple air traffic management example. Something's happening, in this case in the Atlanta area, and you might have low ceilings at the airport. They'll reduce the arrival rate. You might have weather that's occluding the fixes that supply that traffic to it. And if you go through and say, well, I could control with a ground delay program the arrival rate over the next, say, 4 to 6 hours. I have a variety of start and end times, hourly rates. I can decide which aircraft are in there. I can put in-trail spacing restrictions on the or time-based metering on those fixes. I can decide to ground stop traffic into Atlanta for a while. If I just go through and enumerate those possible design choices, you rapidly get into the billions, trillions of options. And they do this today, and they just make those decisions, based on their sort of intuition and experience. And then you take that against the fact that you have variation in the weather. And so we actually have forecasts now that are ensemble forecasts, that they generate a whole series of possible weather outcomes. The one we used for this happens to generate 26. And so the question is, over all that possible range of outcomes, what are the best designs for solving that problem? And all the things we've tried in the past, we've actually been able to solve it and come up with reasonable solutions, but the compute times range in weeks, which obviously isn't terribly practical for a real-time system. But using AI methods, actually using a method that was tested to play StarCraft. We adapted it to this, and it does find a reasonable solution for that. So there is some promise that we can finally bring some science to the traffic management process, and it's time because the system is now entering a period of change that we haven't seen over those 31 years. Amy mentioned, tube, aircraft, standard commercial aircraft. That's been the bulk of the concern of the FAA and the aviation community, for all of that time, and that's really beginning to change. We have small UAS, at the low end of the spectrum, small unmanned aircraft, Amazon package delivery type things, and so on and so forth. That's a new operational design. Urban air mobility or aircraft, such as Brian's potentially going to talk about, eVTOLs and air taxi type things, which are potentially revolutionary for short range and for regional mobility. The tempo of space launches, you probably noticed, it's gone up radically. We're now launching almost every day. And every space launch is a challenge to the airspace. It blocks a bunch of airspace and so on. And so, at high altitude, we're potentially going to start having supersonic aircraft that behave quite differently from traditional aircraft. And so, in the face of this, if we're going to maintain and achieve the economic benefits of these new types of aviation, we have to really improve the way that we handle traffic. And not only that, the traditional FAA model, where we talk to all the airplanes, is no longer viable, right? And so, some of these operations are going to have to be handled by private service providers that will have to deconflict, for example, these small package delivery aircraft. And the FAA is going to have to be comfortable enough with those operations to certify them and say that that's okay, that's safe enough. So if you're looking for problems to solve, on this slide are lots and lots of problems to solve, a lot of great thesis topics, and I'm sure John can tell you which ones are most important. So, not the supersonic. No, that's good. So, just back to what I learned as I tried to apply those lessons. Human-centered design is hard. Over the course of trying to get things deployed and understanding how they would work in the National Airspace System, we've gone through a whole bunch of experiments, some of which were inspired by those original experiments we did on that Iris 2400, which I found a video about it where it said it could render dozens of polygons several times per second, which I thought was excellent. We have better tools for that now. It's still a challenge. A lot of times you're introducing a decision support system because you want people to essentially do their job differently, and they're only going to look at it and say, how can I do my current job quickly, more easily, so on and so forth. That's a challenging problem. Traffic management is governed by uncertainty in weather and demand and so on and so forth. And the science of human-machine teaming, again, perfect segue, has come a long way since 1951, but we still don't understand it completely. How do we work with AI-supported systems in a way where the human is still maintaining sort of central command of the task and the understanding of the task, but is doing it much more efficiently? And interestingly, it's still all about weather, and the weather is getting noticeably worse. The severity of thunderstorms is increasing. Incidence of turbulence is increasing significantly. We're getting, obviously the world is getting hotter. Over those 31 years, there have been a couple of examples of aircraft that had to be recertified to take off at higher temperatures because we now have higher takeoff temperatures at some airports. And that's not going to stop changing unless we radically improve our environmental consciousness. And I'm still having adventures in publishing. I've gone from we still do the thing with the abstracts, but I now am an editor-in-chief of a journal, so I get to really appreciate some of the things that people are doing out there. And those adventures now have gone to getting texts that are written by AI, which isn't as useful an application, I don't think, as some of the ones we were just talking about. But in any case, that's what I have, so. Thank you.
How are you not going to walk around? Because that's, how do you know that? No, okay. Hi, so my dad was a priest, my late father. And so he always said a sermon, you have to have three things. So I'm going to do three things with three different stories. So the one thing I'm going to talk about problems where you can trace the impact, how to have big impact on the world in the environmental space. Second thing I'm going to do is going to show the lineage or how it dated back to work with John. And the third, because it's my nature, I have to rib John just a little bit, because it wouldn't be me otherwise. So I'll start with this, which doesn't seem like aerospace engineering, where it takes a pebble to make a pearl. And the thing about the pebble is a foreign body. Well, for most of us, that's our John Hansman. It's still my line. I'm not saying he's an irritant. However, I do say that his demand for critical thinking has been the pebble that has made many a pearl. And forgive me for focusing on only two of these pearls, or three of these pearls, but those are closest to me, so I can speak most authoritatively about them. So the first pearl is the work that's been done on environmental considerations in approach and landing. And I still remember the day when I got back from JPL, and John said, what do you want to do after I finished my master's thesis, which was on quantum receivers, definitely not aerospace. And John said, what do you want to do? And we started talking about new R&R procedures and GPS and what you could do with that. And we started coming up with the concept of using GPS and R&R procedures to change the way we operate airplanes to reduce noise. So there's been some earlier work done in the late 60s, early 70s, but they didn't have the kind of capabilities that we had at the time, which compared to these days is even baby compared to what we have these days. But at that time, it was state of the art. And so there was one thing that, in addition to critical thinking, was a holistic view of the problem. It wasn't just putting something in a numerical simulation and running it. It was actually bringing the human-centered design, which both Amy and Craig spoke about. And so we created this tool called NoiseSim, which was basically a lot of algorithms in one side, and then our PATAR simulator, which you've heard about before. And I think we've reprogrammed the autopilot and that thing multiple times for different projects. But we were able to do human-in-the-loop studies looking at flight procedures. And so instead of having what you have on the bottom right, which is the standard air traffic control procedure where you level off and come in base leg and turn on final intercept from below, we were able to start the descent from much higher altitude, keeping at throttles. And on the top right, you can see what resulted from our studies. This is the arrival into New York. The left image is the one for the current procedure. The one on the right is the one for the procedures that we end up designing for New York. As you can see, the contours are way smaller. That said, we still had that caveman, chiseling away, complaining about the noise. So noise stayed with us forever. And I'll get back to that when I get to the third problem. So after that work, what John and I did, I ended up, when I joined the faculty here, had a student, Li-Ling Ren, and we took that work, and then we did some flight tests at Louisville in 2000 and 2002. And we developed a very rigorous simulation that we could actually model the wind fields and all the aircraft dynamics, and we're able to actually predict how far apart you needed those airplanes so that they could be at idle from the top of descent to the runway, and not run into each other. And we did the flight test at Louisville, and I've got to tell you that there is something about doing numbers and trusting them, because the first night I wasn't there, and we told them we need these airplanes 15 miles apart. And they called me before, you sure 15 miles? It's like, Li-Ling says so. I've looked over the calculations. We're going with 15 miles. Trust me, my fingers were crossed, my toes were crossed, everything was crossed, but it worked out. And that experiment basically showed, and we had a bunch of noise monitors around, how we could significantly reduce the noise contour, again, like we did in the numerical studies in the lab. So we moved from the lab to prototype and field test. But we also found out that there were incredible benefits in terms of fuel savings and time savings. So it went from more than just noise, it now become how do we design approach and arrival procedures to deal with the environment. So following on this, when I moved to Georgia Tech, we did it basically took that flight trial, we made some improvements in how we specify procedures, and then we end up designing the arrival procedure, which everybody who has flown to LA since 2007 has flown, which basically is the river arrival into Los Angeles. And this one, we had to actually then, going now beyond just the higher fidelity simulations and all the modeling, we now had to do things like, if you're going to change the procedure, you have to make sure that the pilot doesn't have more than 4 or 5 button pushes. Because if you have them down on the screen in their mode control panel, button pushing to change your runway from 25 left to 25 right, you're going to have some safety issues. So we had to incorporate all these things. And again, even though I wasn't on the safety side like Amy was, the lessons that we learned in ASL, now ICAT, basically helped us design this procedure. And what you can see now at the bottom right, and I won't go into the details of all these slides, we were able to meter this traffic coming out from Arizona, and we were able to keep these airplanes and optimize their speeds. And the bottom left, you'll see basically how all the simulations we did to make sure that every aircraft type could stay in VNAV mode from top of descent all the way to the runway. And on the right, you see the savings, that we're saving about $22 billion in benefits in 2018. And this procedure is now spread across the world. So from that conversation and a concept, from lab through prototype to the real world. And it continues because my student and his student, John's grandchild and his great-grandchild, went on to do work and develop some POM MDP algorithms to actually jointly set the spacing and the sequences for arrivals. And this can be executed in Excel. Again, making it simple. So that's a pebble that's turned into a pearl. Another pebble that turned into a pearl is in surface operations. And this was in 1999, and there are a couple of people who are in the room here, Husni Idris, Yanis Anagastakis, John Amadeo, et cetera, who were involved in this project. This was the Departure Planner project. It was a blue sky look at how do we change surface operations. And so much of the work there was actually analyzing the operations at Logan at different airports and seeing and also looking at the ACARS reports to see where were the biggest sources of congestion, what were the constraints. And everybody would say, well, gates and their runways. But on the bottom left was probably one of the most interesting results, that the air traffic controllers were themselves a constraint. Because there is a flow of aircraft on the surface, but in the air traffic control tower, there's a flow of flight strips. And when an air traffic controller is overloaded, they're going to say, wait, I'm not going to give that command. So the airplane might be ready, but the air traffic controller isn't. So those two flows have to be synchronized if you want to have a properly functioning system. And we're doing stuff on electronic flight strips, et cetera, to try to deal with that. But we also saw some other interesting results. The middle one at the bottom shows this behavior which became swapping. So when you push back these two airplanes at the same time, it's a race to an intersection. Any uncertainty in the taxi speed gets magnified because if I get in front of you, I have a minute or 45 seconds at the very least ahead of you before I take off. So for years, we couldn't figure out how to accurately predict taxi time. That swapping behavior allowed us to actually be able to, in fact, Husni, to actually figure out how to better predict the taxi times. And then, of course, on the bottom right, you'll see that there's nonlinearity. The more you push on the aircraft out in the system, is the more congestion, the more delay, and the longer the taxi times. And we actually saw some interesting behavior, Nicolas Pouget and Ferran, that actually the throughput actually went down. It didn't just stabilize, but when you have too many airplanes, it's just total chaos, and you have blockages, and the throughput went down. So this led to the work that John went on to do with HAMSA and Tom Reynolds et al. At the pushback rate, and I got this picture courtesy of Bill Latant via HAMSA, of them at Logan, again, from concept to field trials, where they actually did regulate the pushback rate to keep the rate of the number of airplanes that are taxiing out. And you can see top right, all the airplanes in green piled up at Logan. Bottom left, basically you see a much cleaner taxiway and a shorter queue. And you had significant savings in both time and fuel burn, et cetera, from that as well. Now that continues because now NASA is actually doing a much larger field trial and actually implementation and daily of ATD2, where they're doing a technology demonstration, where they're actually doing this rate control for Charlotte and a bunch of other airports, and Tom and Hamza are still involved, basically doing analyses and determining on the bottom right, basically what the optimum amount of buffer that you could need to put in there to determine to manage the uncertainty. So, again, from the concept through the prototype to basically real world, from the pebble to the pearl. So 2 pearls. So let me talk about the last pearl, which doesn't have a direct Hansman trace, but it has through academic lineage. And this is looking at eVTOLs and urban air mobility. And how do we deal with environmental and noise in particular, because turns out that FAA person is still, that Neanderthal is still there, still chiseling away, complaining to the FAA about noise. It's top corner there. See? So when you look at integrating the cool new airplanes that John Langford and Brian are bringing to the world, into the urban environment, there are lots of challenges. Of course, noise is one. There's safety. There's availability of takeoff and landing areas. There's scalability of the air traffic control, and Craig talked about that. And there's also the ground and communication infrastructure. All of these things exist. But the one thing that when you do the analysis and you speak to people who are in the industry is that noise persists no matter what the level is, right? Even if it's just one eVTOL or one aircraft flying over your house, people are still annoyed, right? And then you have multiple of them just annoying more and more people. By the way, I do want to invent a new sport for the Olympics called drone shooting. And you should have one set of programmers programming the drone to avoid the shots, and another one program it to be a great. You have offense and defense, so you heard it here and that. So one of the things that my postdoc and some of my students and I have been working on, and also colleagues at UT, is basically looking at a holistic, again, back to that holistic viewpoint that we were all taught by John, and looking at how do we manage noise, but we also have to think about how do we manage energy. And how do we also make sure that we fulfill the demand that we have, all right? And so we came up with this network flow problem where we're looking at Austin, Texas, because we know a lot about Austin, and we're right there. And we created basically 3 air routes that basically mask or over highways or cut across neighborhoods where you have significant industrial areas, or you had differences that sometimes it's easy to fly over, other times it's not. And then we looked and said, how do we optimize all of these jointly for noise, energy, and for package delivery? And the way you can do it, limit the operations, right? If you can't fly, you're going to limit. Or you can go to higher altitude, it's going to cost you more energy. Or you can fly along routes where there's noisy, like highways, et cetera. And so we did this, where we had created this network with 63 OD nodes, 3 cruising altitudes, 270 directional links, and 19 vertiports for the city of Austin. And we basically studied, and I won't go into the equations. I hit that slide because it's a nonlinear optimization problem. But in the end, what you get is you can see here how the noise and the energy usage change as you basically give different weighting functions to what you want. So if you have no noise control, these vehicles are going to just fly at the lowest altitude they can, basically from A to B, and they'll make a lot of noise. However, if you have more stringent noise control, you can see here that the community noise exposure is lower and the reaction of the community is going to be lower, but you won't be able to fulfill as much demand. And so we also looked at prioritizing noise and prioritizing energy and seeing how those traded off. And then finally, we looked at some nice theoretical, issues of matters of fairness, whether it was utilitarian or egalitarian, and we showed how bad it is. So we have developed a tool which basically can allow you to determine how you network. So with that, see, I'm stating my thing. I want to summarize by saying it really does take a pebble. And that pebble, in the form of R. John Hansman, has 2 really, for my mind, critical attributes: critical thinking and a holistic viewpoint. And to my mind, these skills are critical for us going forward in tackling the really important problems that we have in aviation today and tomorrow. Thank you.
Stand by. Wrong document open. All right. Aviation in the age of John Hansman. The first thing I thought about this, especially from the perspective of aircraft design, is what is the age of John Hansman? So, John Hansman, as we all know, 70 years old. That's one Hansman. And you all may be thinking, hey, John's not going anywhere. And it's true. John's not going anywhere. But MIT has a long and proud tradition of making up units. And so I would refer you to smoots. When they were defining the smoot, no one said, hey, smoot might get taller. They just painted the lines. And so I'm painting the lines. And so one Hansman is now henceforth 70 years. So we're going to talk about one Hansman worth of aircraft design. We're actually going to talk about two Hansmans worth of aircraft design. And because you all know that I am a future thinker, and I'm actually up here to talk about the future at a lecture that's about history, we're going to talk about three Hansmans. So my job is to use history in this Gardner lecture to forecast what the future might be. So if we actually go a little bit over two Hansmans ago, the Europeans first started thinking about flying machines, actually the Brits, Cayley and Henson there, and of course Lilienthal, very initially successful attempts to fly gliders, unpowered aircraft, and of course Lilienthal, after thousands of flights, ended up unfortunately in an accident of his own creation and ended up dying in flight. Following those in the late 1800s, groups of engineers got together in Europe, and they started to think about how do we actually power these things? Because people had started to realize that flying machines were possible, but it wasn't so obvious how do you power them. And so that was the first International Aviation Congress. And I found this very interesting too, is before airplanes actually worked, lawyers got together and figured out in the late 1800s how to regulate them. That's actually true. You could look that up. I checked it a bunch of times. JT, you're going to have to, if you don't believe me, blame JT. So what usually happens when the Europeans get thinking about things is American entrepreneurs showed up and made it real. And this is my version of history. And so, of course, the Wright brothers in 1903 were inside of the two Hansmans now, followed by the first autonomous airplane. During World War I, these aircraft actually went one direction. They did not come home. The first commercial aircraft, the U.S. Mail Service, of course, started to fly these. And a little bit over 20 years following the Wright brothers, we, of course, Charles Lindbergh, flew across the Atlantic and reduced the time to cross the Atlantic by an order of magnitude. And I bet you that when they first flew, the Wright brothers, no one thought that that was possible 20 years later. So that's 20 years later. Let's keep going. 1930s, Frank Whittle and the first jet engines start to appear. 1940s, I'm skipping over a lot of history. Many airplanes in World War II. Of course, we ended up breaking the sound barrier in the first supersonic flight in the X-1. In 1952, the world's first commercial jetliner. Okay, so that's the first of three Hansmans. 1884 through 1954 was really defined by invention and wartime innovation. We went from the Wright brothers through two world wars, radial engines, tapered wings, retractable landing gears were invented, aluminum airframes were invented, we had the first radio navigation aids, we had refinement of the first flight decks, we broke the sound barrier, we invented jet propulsion, we had rocket propulsion. I can go on and on and on. Okay, what's the second Hansman? So John Hansman was born in 1954, which happened to be the date of the first flight of my favorite airplane, the Boeing 367-80. This was when Boeing was incredibly bold and bet the entire company on the prototyping of a jet airliner to prove to customers and to themselves that this was a product that could meet what the market needed and would create a whole new industry that people had started dreaming about around this time period. So 1954 is the first flight of that prototype. 1957 is the first flight of the commercial variant, the 707, which ends up going into service. Competitors start to show up, the Douglas DC-8, 1958. The 1960s are so unbelievable. I had to just double check the facts here again. Imagine living in the age of this, where 1963, the first flight of the Boeing 727 starts to cannibalize the airplane products that they had just created. 1967, the 737 was flown for the first time. 1969, the first wide-body airplanes, the 747, opens up the whole world, global connectivity. 1969, supersonic flight. Sorry, John. Maybe a little bit of a fool's errand there for a little bit. It can't all be straight down the middle. Yeah, exactly. This I will recognize is an aviation-centric talk. I'm talking to MIT Aero Department. A bunch of space stuff happened. I'm not going to talk about it. If you're interested in this, once again, please talk to John Tilko, sitting right in the center here. He will answer your questions about that. Things happen in space. 1970s, Airbus. Airbus shows up, A300. So wide body, 1979, MD-80. 1971, entrepreneurs start to show up. Herb Keller creates this radical new idea in Texas for a low-cost commercial airline, and he was trying to figure out in that version of the regulatory environment, how do you even make this thing possible? And so he was. Look up the history of Southwest. It's incredible, the things that they were doing in Texas only. Of course, followed up by 1978, Jimmy Carter, signing the Airline Deregulation Act, which created a whole new world for commercial aviation. 1980s, Airbus A320, the first glass flight decks and digital fly-by-wire airplanes. The rise of computerized reservation systems and revenue management. Of course, the MIT department here ended up playing a huge role in the mathematics behind revenue management and all the systems that we use today for those. The rise of turbofans. So turbojets are going away. We've discovered that we can use high bypass ratio fans. CFM is created. Boeing creates two new airplane products in that decade, the 757 and the 767. I'm not going to keep doing that because you'll get tired of it. And it also turns out that from 1990 until today, it's actually very difficult to continue doing the decades there. What ended up happening following the 90s, of course, the 777, the 787, the A350, so on and so forth. From 1990 onwards, it was just relentless innovation on so many fronts across the Breguet range equation. So if you just go back to first principles, it was higher bypass ratio engines, it was geared turbofans, new materials, advanced combustors, low noise. In the engine space, in the aerospace, it was CFD, fuselage shaping, winglets, supercritical airfoils, vortex generators, and structures. We created computer-aided design. We used composites and automated fiber placement machines. That's just on the Breguet technologies. You just heard so much from Amy and the other presenters about the pilot-supported automation tools. We had more fly-by-wire. We had glass flight decks, auto TCAS, ETOPS. ETOPS started to make the world connected in a much more a better way. We had HUDs, GPS, wide area augmentation systems, precision nav, on and on. Market trends, globalization, airline consolidation, LCCs. I can go on. What does it look like in the data? So from 1954, the year that John was born, till now, we went from around 0 commercial passengers, approximately, it wasn't 0, to over 4 billion annual passengers. I cut off the pandemic there because of the big dip, but just to make the point, since 1954, fuel efficiency has improved by over 80%. Since 1954, many airlines were created, many airlines were consolidated. Since 1954, all that revenue management work turned into much better utilization of the airplanes. This is load factor over time, and now, which is over 80%. Since 1954, prices have come down substantially, even through world events where you would think that prices wouldn't come down. Since 1954, Amy just showed us, accident rates have come down. And if you take away some of the other bars there and you just look at it from 1970, the trend is even more clear that accident rates have fallen dramatically. So during that Hansman, what does that look like? That looks like global connectivity, safety, and efficiency. That's what that era is all about. It's the dawn of commercial aviation. It's the invention of every single airliner happened during that Hansman. The scaling of a whole industry, the optimization of all the operations, the global economic impact of building all those airplanes, of running all those airlines, the safety improvements that we talked about, the relentless technology optimizing, 9/11, which was maybe the biggest impulse into the system from a safety standpoint, from an operational standpoint, airline consolidations, the market maturity, and ultimately delivering a system which I still view as a modern miracle. It's really cool. I still, to this day, get really mad when people close their blinds when we're on an airplane, because I want to say, thank you for clapping. So I want to say, don't you get it? Didn't you look around? You're paying $100 to fly across the country in a tube in the sky at 500 miles an hour. It's amazing. So that happened during that Hansman. What happens in the next Hansman? All right, that's what I think my job was here today. But I needed to get through all that first. So I think I reflect on that and I say a lot can happen. It's hard to say in one Hansman. I just keep laughing now. A lot can happen in one Hansman. And it's really, really, really hard to predict. If you started at the start of that, you would not possibly end up at the end of either of those stories that I told you. But it's a fool's errand. It's what my job is here. I'm a fool and I'm on an errand and I'm going to make predictions anyway. And so I think the next Hansman is about these three things. I think it's about sustainability. And I think that, and the way I view that is I think that efficiency still matters. And I'm going to talk about what that means briefly. But getting to zero climate impact, I think, is going to end up mattering more over time. I think it's going to be about autonomy, both automation, where, to Amy's point, humans and automation are working together, both on and off the aircraft, including in the air traffic control environment. And I think that we will start to see the rise of autonomous aircraft, commercial aircraft, over this Hansman. And I think that we're going to see really amazing combinations of these things that are just simply impossible to predict, standing at the start of this Hansman and wondering what it's going to look like at the end. Okay, so on sustainability, today, 39 million annual flights, 1.1 gigatons of CO2 equivalent emissions, and 2.5% is aviation's share of global emissions. Despite all the unbelievable miracle of science statistics that I just showed you, aviation's emissions have been rising despite the 80% fuel efficiency improvements over time. And that's because growth in aviation is outpacing our ability to make the aircraft more efficient. And that growth is good. It means that people want to travel. We should still continue to allow people to travel, but we've got to pick up the pace. So aviation's share of global emissions is actually growing over time, despite all those improvements that I just mentioned. It's not because aviation's not improving. Again, it's because we're flying more than our improvements are coming in. And also, many other industries are decarbonizing faster than aviation. So this number is going to keep going up. Our 2.5% today is going to be a bigger number tomorrow, and that's a problem. So where are the emissions? John and I had done quite a lot of research in this when I was in ICAT. I actually took this more recent data, 2019, from the Cascade team, which I'll give a shout out here in a second. But this is aircraft a histogram of flights by aircraft type over certain missions, and you could see that most of the available ton kilometers in the system are provided by wide bodies and by single aisle aircraft, obviously. So if you start looking at where are the potential emissions reduction opportunity, I'm obviously going to talk in just a second here about the opportunity of electrification and some other things. And if we look in the, call it sub 500 nautical mile space, it's about 14% of the total emissions. And so this is great. We have a lot of innovations that can start to address this market space with electrification. There's a huge addressable flight opportunity, which makes it a great business opportunity, and that's why you see a lot of companies coming into this space, because man, that's a lot of flights to go potentially try to address. But it has a disproportionately limited impact. Even if we electrify every single one of those flights, we've only solved 14% of the problem. We have another 80% of the problem to go. So where are all those? And I can go on and on about this subject, but I'll just briefly say, if you look at wide bodies as just one example, they're somewhere around, call it half the fuel and about 10% of the flights. So if you want to address the problem, you have got to address how this segment of the market is powered. And it's not just how the emissions out of the tailpipe of the aircraft. One of the things that we've been doing in ICAT especially, and what you'll see in a second in a tool that I'm about to show you, is that we have to think beyond the aircraft. We have to think about aviation as a system of systems problem. Where do you get the source of the energy? How do you carry it? How is it transported? How do you use it on the airplane? And ultimately, you get to the total climate impact. So how do we do the full life cycle accounting of all the climate effects? So something that the Boeing team is now leading that I was really proud was really a derivative of the work of I think now decades of thinking in ICAT, is how to create tools that bring all of that together in a quantifiable way that is truthful, that's based on the facts. It's not based on people's feelings about sustainability, but it's based on the literal facts of doing all the math of the system that I just showed you. And that's a tool that's now online, and you can go check it out. And one of the results of that is that it's going to take a lot of different tools. So here's just sort of a very simplified view of how I think things may play out in the next Hansman era. I think there's going to be very obviously new energy carriers on the left. So we're going to need massive amounts of sustainable aviation fuel. That's obvious. There's no way through the next couple of decades unless we have tons and tons of sustainable aviation fuel that doesn't exist today. And that's going to take the form of biofuels, and it will take the form of e-fuels. And there's a whole long discussion about that. And the Lab for Aviation and the Environment, which John now leads, by the way, that lab has been pioneers in thinking about alternative fuels and so on. I think there's opportunity for things like hydrogen, maybe other fuels of this type, and obviously battery electric and electrification. I think we're going to see new aircraft shapes. One of the great things that came out of the MIT department over the last few decades was the D8 program, and that's obviously the first aircraft on the top there, which I'm very passionate about, having spent many years on. I think that we're running out of room on the tube and wing aircraft to make the efficiency improvements, which is why you see that chart that I showed. The marginal improvements are getting smaller, and so I think that there's opportunity for new aircraft shapes. And I think one of the things that I was very passionate about in my PhD research was this idea of right-sizing aircraft, and that's what John and I had spent quite a bit of time thinking about. Can you make aircraft that are tailored specifically for the mission that they're intending to operate? And I think that's where you're starting to see some of what people are calling UAM or regional air mobility or these other somewhat tortured terms. But what you're seeing is aircraft that use particular new energy carriers to be more right-sized for the mission. So that gets to the point where I show you a little bit of what that actually looks like in practice. There's hundreds of companies that are doing things like this. I'm going to talk about the one that I lead, which is the one that's in the red box there, called Whisk. John and Chris Corton is around here. They're going to talk to you tomorrow about the other yellow airplane there called Electra. There are hundreds of these. I just want to show you a little bit about what's going on behind the hood, or under the hood rather, in what are just incredibly fun and entrepreneurial and engineering-driven companies and cultures to build the things that ultimately I think will start to matter for the view of the Hansman that I just showed you there. So we build autonomous electric aircraft. This is there's a long history of the company, which I don't have time to tell you, but this is a fifth generation of one of the airplanes that we built. This one is actually flying down in New Zealand that you can see there. These aircraft take off vertically. They fly like an airplane. and they stop and they land vertically, again, like a helicopter. Our concept of operations is autonomous with human oversight. I'll show you what that looks like here in a second. These are battery electric powered aircraft. The safety targets are when you get into things like doing the ARP 4754 and the FMICAs and so on, things like catastrophic hazards or 10 to the -9 DALE, no single points of failure, so on and so forth. So similar to commercial aircraft. This aircraft, now the problem with battery electric airplanes, and what John will show you as an innovation tomorrow on this, is that they can't fly very far. So this airplane flies less than 100 miles. It carries 4 people. And it charges quickly. These are the kinds of systems that are on board. We are an incredibly vertically integrated company. We make nearly every system on the airplane, which makes it very fun. So it's a composite airframe. It's actually a bonded composite airframe. We use things like Squirtum and some other out-of-autoclave technologies that enable high-rate manufacturing. We build our own computers. We build our own software for those computers. We build our own battery packs. I'll show you what those look like. Electric motors. It's obviously a fully electric fly-by-wire airplane. And sensing, navigation, landing, I'll talk a little bit more about just briefly. For those of you that have an electric car, it's a pretty amazing thing when you really look inside of your electric car. These systems are unbelievably simple. And so here I'm showing just a little bit of what an airplane looks like when there's no fuel in the wings. This aircraft, obviously, it doesn't have a turbine. It doesn't have hydraulic systems. It doesn't have pneumatics. All that it has, in big quotes, is high voltage harnessing, low voltage harnessing, batteries, motors. That's it. Computers. The motors look like this. I think they're unbelievably impressive what you can create with electric machines. This has about the same amount of power that you would get in a Lycoming engine that's on a small general aviation aircraft, and it has very, very few parts. We're in the middle of making all of that right now out in California, and we expect to be flying this first version of the Gen 6 airplane within the next couple of months. But that means that right now we're building all those battery packs. You can see up in the top right there, the battery cells that we use are similar to what's in your cell phone. They're pouch cells that are almost the same form factor as what's in your cell phone. We put them in aviation-safe battery packs, which is a whole very interesting research subject. We make those motors that I just showed you. We put it all on the ground in complex things like Ironbirds and make sure the software works and all the rest. We have to think way beyond the airplane. I hope that you understand that now from the discussions that we just had from Craig and JP and Amy. So these are all the things that we have to pioneer in order to advance our autonomous operations. Trust me, it would be many orders of magnitude easier if we were doing this with a pilot on board. We're really trying to advance all the enabling elements of what the FAA is starting to call the super system for autonomous operations. That starts to look like this. I put this up here because I think this is very interesting to dovetail with what Amy and team just showed, is that the way that aircraft may be supervised in the future, this is an actual picture from how we actually supervise the airplanes. That's the word that we use. All of the human factors for how that's done is new work to do. It's new research. It needs to be done with appropriate human factors so that it's safe. It's a whole new world to go and derive lessons from the past and apply them to the future. We are currently, this is the FAA Tech Center in New Jersey, which was really fun to be back to because I think many of us went to the JUP talks with John at the same center. And so we actually are running simulations with the Whisk airplanes in there now. We take all the sensor packages and compute and all the software and whatnot, and we do things like detect and avoid trials on surrogate helicopters in California using many of the lessons learned that John Langford taught me while we were together at Aurora Flight Sciences. And so it may not stop there. There may be things that go beyond Gen 6, so things like cargo and logistics and other electrified products over time, which is really fun to think about. So bringing it back to our timeline, I guess it is a little bit of a fool's errand to try to predict the future, as I mentioned. But if I have to, I would say it's probably the era of sustainability and autonomy. If I were guessing, and I will leave with this, which is if I look back at that history, what I see is that most of the products that I showed you were the successful ones. But when you really pull the thread on the super interesting innovations and people and projects and companies and all the things that went into creating all of those, almost all of them failed. And I would say that that's probably the world that we're in right now, where it's not obvious what the ultimate landing place is for all these technologies. It's not obvious what are the successful products in this space. It's not obvious what are the successful companies in this space. But John taught us a bunch of stuff, which is thinking from first principles. He taught us to consider the whole system, which I hope you heard reflected from our completely not coordinated talks today. He taught us to do the work that matters, not just publishing papers for publishing papers' sake, but to try to drive those numbers that I showed you on the slides ever higher and lower based on which direction is good, and to adapt to change. And so I think we're all pretty well teed up to go after the next Hansman. Thanks. What do we do now? Oh, I forgot to mention all the slides. That was for Hansman.
Do we have a few minutes for Q&A? Okay. Wonderful. Thank you so much for those outstanding talks. We have a few minutes for Q&A, so I'd like to invite our speakers to come up, and we can open it up to the audience. Please come up. Yeah.
Go ahead, John. Yeah.
No, I'd like to ask John Hansman.
Why don't you take?
Yeah. We have a mic here, but John Langford asked John Hansman, "What does the next Hansman look like?"
No, I think Brian's on target. I think, and actually this is something that I learned in Masha. One of my students, Masha, who's here, is actually the person who got me really to think about the sustainability part. So I think we're fundamentally driven by sustainability as an industry and whatever. And the autonomy is obvious. It's actually autonomy and optimization and whatever. So we're going to think about the objective function. Whether the airframe, I think I agree also with Brian that we should build something like the D8, that we're in an obsolete. We can't continue to go the way we've been going right now. If you get the increased bypass ratio by making the engine bigger, we're sort of at the point where the additional drag from the nacelle counteracts the improvement from that. So we need to take advantage of configuration stuff there. But I think it's existential to the aviation industry, which is if we don't become more efficient, we will become marginalized and will become socially unacceptable to fly. And the market will go away. So I think that's the real driver. Autonomy, I think, is a technology, but we're going to use every technology we can get, and we do need to think of it as a system problem. I also just want to thank everybody. I think there are themes that I didn't realize that I had that I've seen, but I think the goal has actually been to improve the system and to have impact, right? And I think everybody here has. So I think we've done the first part of the job. Okay. I don't know if I answered your question.
No, I'll behave. Brian, this is a question for you. You mentioned that getting the aircraft out there in the world would be orders of magnitude easier if it didn't have to be autonomous. From a business perspective, are you ever tempted to find autonomous market or crewed or piloted markets for the airplane?
Yeah, one of the things that I learned, maybe from John Langford actually, and John, I don't know if this is a lesson that I don't even know if John would agree with this now. But my reflection from our time at Aurora was that the idea of having a piloted aircraft and trying to turn it into an uncrewed aircraft or an optionally piloted aircraft as kind of a pressure relief valve for the regulatory discussion and so on was never dealt with the hard question. It never forced the hard question. By really thinking holistically about the whole concept of operations we think we're able to put forth to the FAA the hard question in a really responsible way, and then should just take it head on. So from a business standpoint, I mean, one of the one of the advantages that we've had is that we've had two very long-term thinkers involved in the company. The company was founded by Larry Page, obviously a very long-term thinker, and then Boeing came in as a joint venture partner in 2019, fully acquired the company last year. So we've been in a position where we can take the longer view, and we don't necessarily have to raise the next round, every month or so. But obviously, the market's changed, times change. You could tell Boeing's in crisis, and so every entrepreneurial journey is kind of, we'll have to take things as they come. So we'll see. But we have no current plan to ever go to a piloted aircraft. We're trying to force the hard question and honestly succeed or fail, and just face into that on our ability to do it. And if we fail, then we're going to fail trying responsibly to do it for the first time, and that's the way it's going to go. Yeah.
I think we have time for maybe one or two more.
So I think this is for Amy. I was just wondering, there was a talk about automation versus pilot monitoring and all that stuff. How often do you think pilot actually does take over from autopilot in the commercial industry right now, that have saved the made it safer, so to speak, in the context of going fully automatic versus not?
Yeah, we're working in the industry to collect data, and we're finding that only about 10% of flights could be conducted totally on autonomy without some pilot intervention. About 26% of flights have some system malfunction requiring pilot intervention to continue safe flight to the destination. And why has this not reliably been logged? Because they're so common. The circuit breaker presses that the pilot does regularly during the flight, that nobody reports it. You say to the pilot, "Why didn't you tell me?" They're like, "Why would I tell you? This happens every day." So the rest include air traffic, wanting fairly quick changes to the flight, disconnect, let your buddy reprogram the flight management system while you hand fly until everything's reconfigured and take over. So we know that, or we are increasingly learning that our deterministic model of the nominal flight is the mean, but the variance around that in the flight, the amount of variance, disturbance, operational disturbance, and variation throughout any flight is profound. And right now, it is the pilot who manages that.
Can I say one thing too? Is I think it's sort of counterintuitive. Also, why autonomous and electric? And one of the things we found through doing the full safety cases and so on is that the fact that we can only fly for less than an hour is actually quite good, because we can operationally restrict so much of the actual complexity of a large commercial aircraft. So I wouldn't want to confound the solving the problem with our small airplane and then saying, oh, therefore it's solved for large commercial airplanes. I would say we are solving such a small portion of that big airplane problem. We're trying to do what I've been telling people is the Fosbury flop, for people that know that term. The guy who first jumped backwards over a high jump bar. We're trying to do that for commercial passenger carrying autonomous aircraft. And the more we could restrict it so that it looks like a gondola in the sky where you take the cable away, that's the better off we're going to be. Yeah.
I appreciate Missy Cummings, who surveyed pilots. This would have been 2018 timeframe, and asked them, how many minutes in your average flight do you actually hand fly? And for the A320, the answer was on 2 to 3 minutes. For the 777, it was on average 7 minutes. This ended up a thing on Wolf Blitzer, where Missy was going, these airplanes are so automated, and I was glad that Missy brought me in as her foil, because Wolf turns to me and says, so we don't need pilots? And I said, well, those 2 to 7 minutes include takeoff, landing, and every emergency.
Last question, anyone? Let's see if we can do this.
For Brian, but for all of you, everyone mentioned the FAA, but not much mention was made of regulation. Is the FAA, in your opinion, as it's currently staffed and organized, able to adequately enable these futures for aviation?
Well, there's a tough word in there, which is, I guess, adequately, or like there's adjectives in there that are hard to describe. I would say that we're headed down the road. From my perspective, just being a developer and seeing the kind of front lines, the FAA doesn't have all of the expertise in the engineering core that's required to deal with some of these subjects because they're so new, and it's okay. It's not because it's a fault of their own. It's because they're incredibly new. So I would say, I mean, this is a National Academies thing that John and Amy and others should, I think, really think about is how can you create an incentive for people to go through some of these really innovative programs in industry and then come back to the FAA so that you understand the technologies that you're expected to regulate? So that's one thing. I think the, from a staffing standpoint and so on, there's just, the FAA isn't the highest performing organization in the world from just like a responsiveness standpoint. I'd say most applicants would tell you that. The people that are really running cert programs would say, my biggest frustration is just, the nuts and bolts of passing paper back and forth and other things. It's less, I guess there's less of a big theme there, but there is this talent problem that I think there's something really there for the National Academies or somebody else to consider. But the air traffic control you should talk about, because I actually think there's staffing problems there.
Yeah, but I do think that there's staffing problems in the cert side too, in that they're trying to run the regular operation, like dealing with all the Boeing issues, while at the same time you have a ton of other new entrants. And so even if they had the folks who had I agree with you, that the expertise, even they had the expertise, they're just overwhelmed because there's so much going on in the traditional certification marketplace that when you have all these new entrants, it's hard to get you basically join the line and get a number. Right, and you probably see that I saw that when I was at Universal Hydrogen, we were doing that. It's just hard to get a number because people are busy doing the Boeing and the Airbus things in the real world. But I do think that air traffic controllers, they have some staffing issues. The question is AI going to be helpful, or do you have to surge staff to basically bring new technology in? And I'll leave that to you.
Okay, I'll just make a couple of quick comments. To start with the air traffic control staffing issue, AI is not going to help that particular problem. What will help is that the FAA is actively changing the rules by which people can get into the system and how the training is going, and we pretty much believe that that's going to start turning around. But it is a challenge right now. The existing controller workforce in only a few places, but in few very important places, is very overworked, and that is a constraint to some degree on the system. But with respect to the certification challenge, there's kind of two aspects to that. One is, the way the certification system works is that the applicants are bringing with them not only this is what we want to certify, but here's the means by which we're going to demonstrate compliance. And the FAA is sort of honor bound in this system to not suggest how to do that. They can evaluate whether something that comes is adequate, but they're not going to prescribe how to do it. The challenge there is nobody knows what's adequate for certain kinds of systems like this. So we're actually holding, I think it might be next week or a couple of weeks, we've been holding these symposiums where the industry comes and FAA comes and experts from other people come and kind of discuss this problem. How are we going to solve this problem? So progress will be made. It will be made at a pace which ensures safety, which is inconvenient for venture capitalists and so forth. But that is, but everyone's trying. I mean, it is a very big challenge. So, we'll just have to hold suit. You have to understand that for the past, 31 years at least, and possibly an entire Hansman, the only thing that the FAA has been asked to certify essentially looks like an airliner, or a general aviation aircraft with, slight variations on where the engines go, and so we did certify the first electric propulsion aircraft about a year ago, maybe. So that progress has been made, but now we're going to bring an aircraft with, 8 rotors and, in some cases tilt rotor and so on and so forth, and then say that that's going to be managed by an AI-based system, and it becomes challenging. So, but we'll get there.
We'll get there.
Wonderful. Please, let's thank our speakers. And also thank John for all his contributions in the age of Hansman.